morning, everyone. I know Oren is super excited to be here, and I am as well. So thank you very much to the NVMe committee for giving us this opportunity to chat about a kind of update on the controller memory buffer and what's called the persistent memory region ecosystem. We're not actually going to get time to get into PMR, even though I think there's an awful lot of amazing stuff that we can do with PMRs. So that one we probably won't even touch because we don't have time. But if you go online and look up my name on the Persistent Memory Summit from earlier this year, I did talk quite a bit about PMRs and how that could be interesting for persistent memory over fabrics. So if that's interesting, you can go look at that, and you can watch that presentation instead of this one if you really want to. So we're going to talk about that, and then we're also going to talk about how the software stacks have been evolving to take advantage of CMB. So, you know, I'm a big advocate of, you know, it's all about the software. And if you don't have good software, the hardware, even if it's really great, can't do anything interesting at all. So one of the areas I focus on is software enablement for interesting features. And the NVMe CMB seemed to me like a feature that was just crying out for software that actually got it to do something useful, because nobody seemed to really know what to do with the CMB. And I had a lot of marketing people from different companies come to me and go, you know, everyone's talking about CMB, but we don't really know what to do with it. So I went, you know what, we're going to go off and turn it on in a couple of different stacks. And we're going to talk about that today. And then show people what we think we should do with it. And then hopefully people will start building more drives with CMBs and PMRs and using them in new and interesting ways. So that's kind of what we're going to talk about today. So Oren's going to introduce us to the controller memory buffers. And then we're going to jump into a couple of potential use cases. So one of them that we have seen actually implemented in the Linux kernel is to use the CMB for submission queues. That can lead to some latency improvements, but it's not particularly amazing. What we think is pretty interesting is using what's called the RDS and WDS capabilities of CMB, and I'll talk about what they are later in the talk, to do what we call offloaded copies. So a very cool way of actually moving data around in an NVMe-based all-flash array without actually taxing the processor at all. And given that these drives are all capable of doing 1 million IOPS each, and you might have 48 of them in a 2U, you probably don't want to put every I/O through the processor subsystem because it just can't handle that. On top of that, when you're doing things like fabrics, you also can't handle 10 million IOPS going through the central processing unit's complex and its memory subsystem. So why not do it peer-to-peer? And we're actually working with some server vendors who are starting to take that to heart and designing their servers in new and interesting ways, so we can do a lot of peer-to-peer from RDMA NICs to NVMe drives without even going through the central processing unit at all. And we'll present some initial results on that. I'm going to talk a little about some of the work we're doing to enable all of this functionality in software stacks, because if the software isn't there, the hardware won't be able to do anything. So we're going to talk a little about what we've done in SPDK, which is a pretty popular user space framework. Notice I didn't swear when I said that. And also we're going to talk a little about the work we're doing in the Linux kernel, also to turn that on. Some of you may have heard of the Linux kernel. It's a reasonably popular operating system. And then we're going to kind of talk a little about the roadmap for the future. So with that, I'm going to hand over to Oren to work through the first 2 slides and then come back to me.
Thank you.
Or Ilker.
So we can switch, right? Okay, so what is the controller memory buffer? Basically, we're talking about just a piece of memory that resides within the NVMe device, just sits there. It was presented in 2013 in spec revision 1.2. And it's announced by the device through registers and a specific bar. What do you want to do with it? You like to either put the data there in between it's going to the from host to the flash, or you can put the queues on it, or you can put both. Okay, so it's just a piece of memory that is exposed to the operating system to do either of these 2 tasks that are in order to accelerate your way to the drive. You'll need 2 registers that are part of the spec to announce that a controller memory buffer is supported. One says where it is within the bar, so you can choose as a vendor to put it anywhere in the bar. And the other just says what's the size of it, plus some indications of what you can do with it. Okay, so not every NVMe device can do everything or want to do everything with this CMB. So there are specific indications whether the device can access data coming from that CMB, or whether it can put the queues, the submission queues, the completion queues on that CMB. So all these bits are part of the same register. And yeah, and we have multiple vendors already supporting CMB. One of them is just here. Yeah, so basically a piece of memory that is accessible through the bar, through the PCI interface of the NVMe device. And that's how it looks like. Well, that's how it looks like if you do LSPCI, right? So when you do LSPCI on an NVMe device, you'll see all that data. And if there is a CMB supported on this device, you'll see an extra bar there. In this case, it's 512 megabytes. Just a bunch of memory accessible to the OS, mapped as I/O space to the CPU, and to whoever wants to use it. I think next one goes to you, right?
Yeah, I think so. Great. So thanks. So that's how one way of telling that a drive has a CMB. The other is inside Keith Bush's excellently maintained NVMe CLI, which I'm sure many of you use. You can push out the registers specific for CMB, and you can get it in either binary form or human readable form, or an application could do exactly what Keith's code does if you want to include CMB discovery inside your application. So there's many ways you can get the data of, do I have drives with CMBs? And if I do, what are they capable of doing? And what could I, maybe potentially do with them? So now that we have hardware that supports CMB, and I didn't set up the company, but I had to basically do a company so I could get the hardware. We wanted to do some fun things with software. I am a big fan of the Linux kernel, but also the Linux kernel does have a cadence to it. So there's other frameworks that we also wanted to work with inside, and one of them is SPDK. But before we get into the actual software, I wanted to talk about some of the fun use cases for CMB. And the diagram that you're looking at on the right here kind of shows, one of the things that I always thought would be fun to do with a controller memory buffer. And that's basically to copy data from one NVMe drive to another without having to go through the DRAM that's attached to the processor that's connecting those two drives together. So on the diagram, I have a left side and a right side. So on the left side, I have the red arrows and what's called the traditional DMA. So if you go into Linux or Windows or SPDK or any other operating system and you say, can I copy 2 terabytes of data from drive A to drive B? The drive does that by DMAing data to system memory, right? So it goes up to the root complex, it goes through the internal bus, it goes to the integrated memory controller, it goes out to the DRAM, assuming you don't have DDIO turned on and you're not using Intel, and there's a few nuances there, but you kind of get the idea. And then at the same time, as soon as you have enough data buffered in DRAM, you start issuing write commands to the other drive, and it starts sucking that data out of the DRAM through the memory subsystem, through the internal bus inside the processor, through its root port, down through the PCIe tree to drive B. And notice that these drives could be sitting behind a switch or multiple switches. They could be in a JBOF, they could be an add-in card. I don't really care, but that's basically what a traditional DMA looks like. You are consuming processor resources, right? You're consuming processor resources in the fact that the NVMe commands have to be executed. That's lines of code. They are running on a core. You're consuming PCIe resources because the DMA traffic has to come through. And you're consuming memory resources, both in terms of bandwidth on the DDR interface and also volume of DRAM. Now, let's say you're a cloud vendor and you're running a whole bunch of virtual machines on those cores, the ones that aren't running the NVMe commands. People are paying you money to run VMs on those cores. That's how companies are making lots of money today. And if those VMs kind of get stuck because they can't access the DRAM because you've got all this DMA traffic going through it, your customers will probably start getting pissed off. And they may go to a competitor who's decided to do things a little different, and they can provide better VM quality of service, even under high I/O load. So there's an interesting use case that we may or may not be talking to people about. So, on the right-hand side, this is what you can do when you have a CMB. You can basically issue a DMA command saying, hey, rather than DMA into system memory, can you DMA to the CMB? And the drive has told you that it has a CMB, and the OS knows where to map it. And you basically pass it into a DMA API, and away it goes. And so that's what you can do, and that's pretty interesting. So that's an NVMe copy, and I'll show you exactly what we did on that. And then so that's use case number 2. And use case number 3, which is also interesting, is, hey, do I really have to do this between 2 NVMe drives? Well, no, I don't. I can do it between anything that has a DMA engine, which is pretty much any PCIe endpoint on the planet, and an NVMe drive of the CMB. So you can take the, and in fact, actually, this diagram was supposed to have been updated. This is the old one, so that's my fault. It should actually say NVMe and NVMe, but it actually says NIC and NVMe, because the reality is that you can actually have any device you like to the CMB. So an interesting one is a fiber channel or an RDMA capable NIC, doing NVMe over fabrics and putting data directly into the drives. And that's what we'll talk about in a minute. Okay. But the thing is, that's the way that it's done today in Linux. If you go and download Linux today and you try and do an offload copy, it will bork. It won't work. It won't let you do it. There are some reasonably good reasons why that is true, and I'm not going to go into them today. But if you go to Linus's tree and you compile his kernel, it will not work. Until Valentine's Day this year, and it was Valentine's Day, which was kind of nice, SPDK would not do this. SPDK, if you downloaded it and tried to do it, it would bork. It would die. On Valentine's Day, the maintainers of SPDK accepted some patches from this guy called Stephen Bates that changed the behavior if you configured it a certain way. And now in SPDK, if you want to do the green types of DMA and you have the hardware to support it, you can go do that. So that's kind of the importance of software enablement. The hardware is pretty useless without software. So basically what we added in SPDK, and if you want, go on GitHub right now, look at the master tree, search for my name, and you should find on Valentine's Day, there's 4 or 5 patches that went in. And what they did is we exposed a new API that said, if I'm moving data from NVMe drive A to NVMe drive B, and if one of those drives has a CMB, and if the user wants to, I'll use the CMB as the buffer rather than system memory. Okay, so now I can actually do offloaded copies. SPDK is a user space framework. It was originally an Intel product. Now it's an open source product, though Intel still definitely have a pretty large contribution to it. It does focus on performance and NVMe and NVMe over fabrics. So a lot of people who are deploying NVMe are actually either evaluating it or using it. There is an SPDK developers framework that I will get a beer for if I promote. So I'm going to promote it. It's later this month. There should be a slide at the end of this deck that kind of gives more details. If you're interested, you should go. Like I said, we added code to turn on this peer-to-peer copy. We also, rather than just adding the API, we added a simple application. This is really just an example application to do a CMB copy. And there's a README file that we added as well that shows you how to do it. It's called CMB copy. So if you want to, you can install SPDK, and you can basically run my example, and it will do what I'm going to show you on the next slide. So this slide is really hard to follow. I wouldn't even get too worried about it. But basically, this is a kind of a screenshot of me doing a peer-to-peer copy. The funny boxes on the right-hand side are actually, we use microsemi switches a lot at Adedicom because they have a management endpoint that has an open source driver, which means I can get things like traffic counters out of the microsemi switch. I can't do that with PLX, so we like microsemi for that. And that means that I can actually visually see, am I doing peer-to-peer? Because it can sometimes be quite hard to work out, are you doing peer-to-peer? Because things are happening very quickly, and I don't always have a PCIe analyzer. So if the switch can tell me that traffic is moving from one downstream port directly to another without going to the upstream port, okay, I know I'm doing peer-to-peer. That's good. It's kind of a sanity check. So what the counters are showing me on the right-hand side of this diagram is just that I'm moving quite a lot of traffic between the two drives, but that DMA traffic is not going to the upstream port. It's not going to the processor. In theory, I could move literally terabytes of data between the drives in my all-flash array, and not a single byte of the DMA data traffic has to go to the Intel or the ARM or the power that's running as the storage node. I don't tax its root complex, I don't tax its internal bus, I don't tax its memory subsystem. As long as the drives support it, I can keep all the data movement down in that lower layer. Okay, so that's pretty important. Oren, back to you for the next use case.
So, thank you. Stephen here was talking about the use case of moving data between drives and themselves in the system. It's very nice, Stephen. But it involves no network. So, come on. Where's the network? Okay, so the next use case is NVMe over Fabrics, of course. And so we did something very interesting in order to bind all those technologies together. So on the one hand, we have the technology that Rob presented just the previous session of NVMe over Fabric offload engine within the Mellanox NICs. Okay, so there's one way that will save you a lot of CPU cycles, right? Because every IO, every transaction from hardware is being directed directly to the next, to the NVMe drive just next to it on the PCI. But you're still moving data. You're still moving data and you're moving it to the system memory back and forth. And we actually saw it with customers who were testing our technology and seeing that, yeah, we have 0% CPU utilization, but our software is still stuck because it's trying to access the memory, which is fully utilized, right? So if you take this technology and combine it with CMB technology, you solved it. That's it, you nailed it. If you look at the last row there, you'll see not only you reduce CPU utilization to 0, you also reduce memory bandwidth utilization due to NVMe over Fabric offload, due to NVMe over Fabric application, also to 0, while sustaining the same IOPS, the same bandwidths, everything that's the same. So this combination is really, really interesting. There was some work needed to make it happen. One of it is a patch set called P2P-DMA, which is being proposed to Linux kernel. So the challenge is telling each device how to access the other device, right? So we have a NIC on one side that wants to shoot data directly to a CMB, which is on the other device. How do you coordinate the two? How do you transfer the addresses from one to the other? P2P-DMA was exactly for that. Is exactly for that, and it's more than CMB, it's more like a framework in which any PCI device can declare, hey, look at me, I have some memory on me, you can use it. So the device registers itself as having some memory that can be used for whatever purpose. Other device drivers can query, hey, who has some memory on this and that PCI switch or whatever. And it can find the other device that was publishing that it has memory on it. So with this framework, the two devices now, the two device drivers, can coordinate and find each other for the purpose of data transfers between them, between the two devices. So these patches are there, waiting to be accepted, I hope, soon. And of course, it's just the beginning because there are a lot more things to be done there. Has to do with mapping the addresses correctly if you're using IOMMU or if you're using virtualization, stuff like that. But the first step is there, and we hope it will be accepted soon. Next one, yeah. Okay, so if you look at the flow of data in this example, which is NVMe over Fabric application, you'll see on the left-hand side the network card, right? This one is accepting requests from the network, from initiators. And the way things used to happen, described by the red arrows, the request goes in, data goes in, goes to the system memory, waits there until the request is going to the NVMe drive, and then the NVMe drive takes the data from system memory, puts it on the flash. Once you have P2P-DMA, once you have NVMe over Fabric modifications to use the offload and the CMBs, you get the green path where data parks on the CMB in the PCI, never leaving the PCI subsystem, and being pulled from there by the NVMe device as soon as the request arrives to the NVMe device. So that's really exciting. And with these two, you can actually see wire speed performance with zero impact on your CPU and memory subsystems. I think the next one is for you.
This is for me. I guess maybe one thing to point out on this slide is notice we didn't have a CMB in every drive. You could have CMBs in every drive. In this case, we actually only had the CMB in one drive, which wasn't even a drive. It was a device that was really just a CMB. It provides some other services potentially, but so there can be mixing and matching here. You could have some drives with CMB, some not. I think architects can make decisions on what are some of the interesting deployment models and mixes in some of these systems. But I think, to build on what Rob and Ilker talked about, they offloaded the processor from running the NVMe commands. This adds to that by offloading the data flow and the memory subsystem. And in theory, you could take that Intel Xeon out of this picture and replace it with something much wimpier and still get exactly the same I/O performance, right? And then maybe we start integrating some of these pieces together. Maybe the RDMA NIC has a controller memory buffer and an NVMe interface, right? Now, there might be some startups doing that, right? So lots of potential for interesting innovation, but without the software to turn it on, the hardware is completely useless, right? So we have to get Linux updated, Windows updated, VMware updated, SPDK updated. It's totally useless without the software. So, speaking to that then, where are we going? What is the roadmap? So, the NVMe CMBs are a hardware construct. They've been in the standard for a long time. I think as a group, like we've all struggled to work out what on earth do we do with these things, right? As we say in Ireland, these little feckers. What do we do with them, right? I think we're starting to realize there are some interesting things we can do, but only if the software stacks enable that, and some of us are making an effort to do that. And that benefits all of NVMe. I think that's one of the beauties about the NVMe ecosystem. We're not doing this for proprietary PCIe endpoint. We're doing this for any NVMe device that wants to participate in that game, okay? So that could be anybody's SSDs can take advantage of this. There's no vendor specificity, what is that a word, whatsoever. Right. So SPDK, we've added the peer-to-peer copy. There's more work to be done there around threading and performance. If you're interested in getting involved, let me know or talk to Jim Harris, who's one of the lead guys at Intel for SPDK. They have roadmaps. We want to integrate NVMe over Fabrics and peer-to-peer inside SPDK, and that's all work that's going. The Linux kernel, the latest peer-to-peer DMA patches are in. They're being discussed. We're hopeful that we'll get something upstream this year, but the Linux kernel moves on a cadence that is interesting. Thank you, Sagi. You're going to make that happen. Maybe, and the roadmap there may be to extend what we expose to more than just memory regions. Maybe we start exposing more resources like NVMe queues, like doorbells. So there's very interesting ways that can go. And that might be done within Linux or within SPDK or both. And then, the last topic is really one that's near and dear to my heart. So persistent memory regions, we really just didn't get time to touch on today. This is really a non-volatile controller memory buffer. So imagine taking these memory buffers and making them persistent. Essentially, that is an NVDIMM on the PCIe bus. Now, that sounds really stupid, except when you start thinking about fabrics and remote access, then suddenly it starts to get a lot more interesting. And then as memory technologies come along that are byte addressable and maybe a little cheaper than DRAM, maybe our persistent memories go from being half a gig to 1 gig to 1 petabyte or terabyte to a petabyte to whatever. And now I can build boxes with multiple very large memory addressable PMRs and access them through a fabric that could be, an RDMA type fabric, or it could be a Gen Z fabric, or it could be an OpenCAPI type fabric. And we start getting to a very interesting space. And I think a question more for yesterday's audience, the people within NVMe on the standard, is are PMRs an NVMe thing, or are they something different? Because they're not block and they're more byte addressable. Does NVMe play that? Does it belong in SNIA? Like, where does that sit within the industry and the industry associations? And I think there's quite a few people in this room, looking at you, Mark, and others who can give some leadership at a high level saying these are the standards bodies that need to go and standardize some of this. And then the software people can go start turning some of that on. So that can all happen. I'm a great believer in doing things for yourself. So almost all the work we've shown today is reproducible. This slide will be available for download. So most of the resources should be there. If you find something, a piece that's missing, let me know, and I'll happily point you in the right direction. Everything we discussed today, I think, is open source. So it's all there and ready to go, not proprietary at all. And so go try it out for yourself. Go to your favorite vendors and get some of the hardware from them. You could beg, borrow, and steal it, and set up some of these systems and have a go and see if you can put it together in new and interesting ways. And then finally, this is for my beer. So if you're around later this month, I believe it's in San Jose, the SPDK Developers Summit is going to be here. If you want to get like a really good instant boot up on SPDK, you may well want to attend. I want to thank Oren for being my co-presenter. And thanks everyone for your time. And I think we have a bit of time for questions or whatever. So if you have any, let us know.
So you said that you could have the CMB. So you said that you could have the CMB on either device. You were going between two drives.
That's correct.
Which would be preferable? Which one is the, how am I going to get the most performance out? How could I play this game to get to do it best?
It's a very good question. I think at the end of the day, the CMB certainly today is typically implemented as a region hanging off the DDR interface on the controller. So if you're using that DDR interface for CMB, that drive isn't necessarily able to get the same quality of service for its firmware that's maybe running part of the FTL and so forth. So I don't know if there's a right or wrong, and I think it would also depend on whether you have drives that are all from the same vendor, and so they have the same architecture, or whether some of the drives are add-in card and maybe have a wider DDR bus. And then it also gets interesting in the sense that I showed you some topologies where the CMB device was not an SSD. And so I didn't show the exact topology, but there's also the case where you can bounce buffer through a third device. And so maybe an interesting one is where neither of those two devices you're copying between is the one with the CMB, and the other one is. So I don't think I have a definitive answer. I don't know if Oren does.
No, I would just point out that it could also be interesting if you think about the CMB on the network card. It's also possible. So.
Now, have you looked at speed grading the CMBs? I mean, you've obviously, when you format to non-binary sector sizes, often the device will say, hey, I do this size well, I do this side less, I do this side worse. Is there some way that we could go through and go, what's going to be my relative performance? Whose CMB do I want to use?
Yeah, so that's a great question. So I think, just to repeat what I think I heard there was, can we potentially advertise capabilities more that we have already in the spec to say, hey, what's my speed grade of CMB? I think that's a very interesting idea. Right now, we don't have that, and I don't think there's any plans for the spec to add that yet. But CMB may get revisited sometime pretty soon here, and that could be something to discuss. But right now, it is pretty much put it in your lab and characterize it yourself. But that could definitely change, and that's a great suggestion. Okay, so Peter, who is pretty much the god, so yeah. So PMR is going to get some of that for the people who can't hear and for the recording. So PMR is actually looking at that, and maybe retroactively CMB picks some of that up as well. So if you want to get involved, you can, if you're not already a member, you can join and you can actually help make that happen if you think it's important for your systems and for the ecosystem in general. So the point there was that micro-semi switches I'd go talk to the guy who built them.
So a two-part question. Unrelated, actually. My first one is really around security with this peer-to-peer. Have you guys really thought about the aspects of security when doing all the nice peer-to-peer stuff?
We had a really good discussion on the Linux kernel mailing list on this topic about 6 weeks ago, where even Linus got, it's interesting when Linus starts getting involved. So that's a very good question, and it kind of relates to something called access control services, which is a feature of PCIe, not NVMe. So what's being pointed out here is if I can do DMAs between the PCIe endpoints without the IOMMU doing any safety check, there is potential for security implications, both for rogue and malicious PCIe devices. So what we're doing right now in the kernel is saying if you are doing peer-to-peer, you're an expert, and you're going to be aware that this is not necessarily something you want to do in a production cloud environment today. The other thing that we're doing is we're talking within PCIe SIG to go, is there things we could be doing in the endpoints and the switches to add windows or some other kind of access methodology that's not just the system agent, IOMMU? So we could actually have, some kind of ACS that pushes further down into the PCIe. Now that is definitely a long-term project, right? Because PCIe would have to define it, and then hardware vendors would have to pick it up, and then the operating systems would have to play with it. So it's a really good question, and you are right, there are definitely implications, and they are being discussed. And right now, it's caveat emptor, for sure.
Part 2.
Yeah. Yeah, so I think, in a storage system, it's hermetically sealed, as Danny Cobb likes to say, and so you can say that for sure, but I think you still have to be aware that you're making that decision, right? As opposed to just not even realizing that it is a decision.
Once I have a rogue device with peer-to-peer capability, even a secure sealed storage system still has the same issues.
Yeah. There's potential different challenges for sure. Yeah.
So my part 2 is really Austin's favorite, and it's really about air handling in this peer-to-peer environment. Right? Where are the fatal layers going? I mean, is it going to the root? Is it going to the guy who initiated the transfer?
So remember, certainly in everything I showed you today, the thing that's issuing the I/O is still the OS, right? So we're not, in the offload, that's not true, but in the peer-to-peer copy, you are still, it's the NVMe driver that issues the I/O, and the PCIe system and AER reporting is set up exactly the same as it was before. The only thing that's changing is the DMA write addresses are no longer in system memory. So that doesn't actually have any impact in terms of how AER is set up or where AER events go, right?
And that goes for the NVMe offload for the network, because you have all the AER set up and you have the drivers in the OS. So if you have peer-to-peer access that has failed, it will report AER to the respective driver, which will take the tear down actions and whatever needs to be done. So it's all.
But both very good questions. Very good question. Thank you.
Recovered on that. And so if you had another peer device then sending that transaction and it got, say, detected at the downstream port above this other target device, are there the mechanisms so that will get reported up to the host and we'll know how to handle that one. Yeah. How will it know to handle the guy that sent the transaction?
You'll need to close the loop between the two. Okay, so you need the driver that owns the NVMe drive that generated the error to talk to the driver that is responsible for the NIC.
That's code that hasn't been done yet.
It has been done in our case, in the NVMe Fabric offload feature but it's not upstream. So it's open code, but not upstream yet. But you definitely have to close the loop. You have to synchronize the two drivers to respect each other and let each other tear down what they need to tear down. Yeah.
Why are you encouraging to have CMB space either on a drive or on a NIC when it would probably be better to have a RAM drive adding card? I mean, why would we ever want to put this on a drive?
I think PCIe lane count would certainly be one. So in certain topologies, you just don't have a spare slot. But we're definitely talking to customers who are interested in both just integrating us into a bigger endpoint and also just using us in isolation basically as a CMB that can also provide some other services. So both are interesting.
So this looks similar to, hi, I'm here. So this looks similar to the GPU Direct that NVIDIA has proposed with GPU Direct RDMA and general peer-to-peer GPU traffic. And one of the reasons that was not accepted, I mean, it's there since 2014, 2013, they have been vehemently going after that. But Linux is not adopting that technology for two reasons. It's for they're modifying the get user pages API, which is kind of breaking the kernel methodology to be vendor agnostic. So does this require any modification to the kernel, the way NVIDIA is proposing using UVA?
No, so it takes a pretty different approach. And I think there's two main reasons why there was a lot of pushback on what Mellanox and NVIDIA were trying to push, and Oren may have a different view than me because he works for Mellanox. But, NVIDIA, just because of their binary driver nature, that was pretty much like a no, like right from the start, right? Why should we support somebody who's not willing to open source their drivers? The other one was because it's a graphic card, they tend to want to be able to take that memory back. So they needed callbacks that basically said to the people who had borrowed the memory, hey, you can't have it anymore. I need it because I need to do some AI inference or whatever. And that callback was an absolutely horrific path. It was very proprietary. And it was basically only going to work for Mellanox devices and NVIDIA devices. Whereas the framework we're proposing now is completely general. Any PCIe driver that wants to can play either as a consumer or a contributor to the memory pool. And we don't use any of this UAVA stuff at all. Okay. In fact, we leverage a lot of the zone device work that Intel did with DevM, memory map, and so forth.
Okay. Thanks for that. So related question is basically for the Peer Direct, the obvious condition that Intel has is basically two devices has to reside behind the same root port. And as well as you still need to share the PCIe devices, PCIe lanes, which are going to the same root port between the devices. So essentially you're impacting on the bandwidth utilization because of that constraint, as well as you're now enforcing that you need to increase the CPU PCIe topology behind the same root port. So I think this will also fall in the same category because this has nothing to do with the NVMe device, but the platform as such.
Well, I think a lot of people are building like fan-out systems for NVMe, which have PCIe switch topologies anyway. So that becomes a very amenable platform to deploy this kind of peer-to-peer framework in. Your point is well taken. So right now, certainly the Linux code, the SPDK code doesn't do any such checks. So it'll work as long as the physical hardware supports it. But the Linux code we're proposing doesn't allow a peer-to-peer transfer between two root ports off the same root complex for the simple reason that we can't guarantee in any PCIe standard way that the root port will let that happen. So sometimes it happens and sometimes it gets blocked and sometimes it goes through but with poor performance, and it's very architecture dependent, and even within Intel processors the characteristics change. There's actually some discussion within PCIe SIG to maybe go address that and have a capability register added. Again, this would take time to permeate into real hardware, but at least to go to the standard and say, you can either say that you don't support peer-to-peer between root ports in the same root complex, or you do. And again, there's some discussions around fine chain control that we might add at the same time. So that it's a very good point, but we just have to be cognizant that if we put out kernel code that's just going to be very, very flaky across architectures, we'd have to pay a price for that. And I know there was quite a bit of discussion on the mailing list about that as well. And so, we are where we are, but we can certainly move forward in a few different ways. Okay, great. And the great thing of it is the kernel code, you can always hack it yourself and get it to do whatever you like.
Okay, great. Last question on that. Thanks for that. So NVIDIA is proposing something like GPU Direct Async, where the NIC devices can directly post the work keeping CPU away. So that will further reduce the CPU utilization. So in this case, are you planning to have something like a queue pairs also exposed to the bar so that the NIC can actually post the work and then get rid of the CPU completely, other than just setting up the queue pairs? The the NIC can actually get the work done, or even the opposite. The NVMe device can do the work, vice versa.
That's exactly the feature. That's the NVMe Fabric offload.
Okay.
Yeah, that's exactly what you do. You could take away the CPU. Once you need the CPU to set up the connections, program the queue pairs, program the connectivity between a queue pair and submit complete queues on the NVMe. So you need all that. You need the CPU for that. But once you have connection established, you could actually plug out the CPU. I mean, conceptually, right?
No, that's right. But in this case, the devices need to be aware about the bars and the locations of the queues and the structures, right? The descriptor formats, things like that. So
yeah, so you need it to set up everything. But once you have a connection established, you have a full data path going directly from NIC to NVMe drive and back. Okay, you need to take care of exceptions. You need to take care of new connections, tear down of connections. There, you'll do all that, all admin commands, all that. Of course, you keep doing on CPU, right?
So does the Mellanox device does today, right?
Yeah, from ConnectX 5. And,
okay.
The blue.
Okay, great. Thanks.